Hey y'all, welcome back. In tonight's homework, we're looking at logarithmic equations. We're going to be rewriting equations in logarithmic form. We're also going to be rewriting them in exponential form. And so that's what the homework starts with, is just trying to rewrite all these logarithmic equations in exponential form. Once you kind of know how to do it, these should go pretty quickly. And it's always a good idea to check, maybe not every single problem, but every once in a while, to make sure that you're writing it correctly. So just to be clear, when you have an equation that's written in logarithmic form, so like let's say we have log base, we'll just give it a name here like A, or you know what, let's use B for base. So log base B of, let's say, x equals y, okay? So if I want to rewrite this equation in exponential form, the first thing to realize is that anytime you have a logarithm, okay, a logarithm is just an exponent. That's what a logarithm is. So this y is going to be the exponent in the exponential equation. The base will always be the base, okay, so the base is the base in both cases. So we have b to the power of y, remember the logarithm equals the exponent, and that should equal x. Okay, so basically you're going to rewrite this using exponents, and the equation should make sense. So like for number one, the base here is 3, the power is 2, and what it actually, or I guess the exponent is 2, so the power would be 9. So 3 squared is 9, so we could do a quick check and see, okay, well, yeah, that makes sense. 3 squared is 9, so this seems correct. For number 2, we've got 4 to the first power is 4, okay, which is true. And what we're looking for are any false statements that we might write. So 6 to the 0th power is 1, that's true. If we ever end up with a false statement, either we rewrote it incorrectly or the equation to begin with just wasn't true. I think all of these work out nicely, but we'll just kind of go through and check them as we go. So here we've got 7 cubed is 343. Okay, that's true. For number 5, which looks like a repeat of number 1, maybe I got a little copy paste happy here. Are there any other repeats? I don't know, but I see 3 squared equals 9 again. My bad there. Here we've got a negative exponent, so this might be worth just taking a moment and trying to explain, why this is true. Anytime you've got a negative exponent, let's say you have like x to the negative a power, that is equivalent to 1 over x to the positive a power. So that's how negative exponents work. One way to think about it is, when you're first introduced to exponents, you think about it as repeated multiplication, right? So like, what's a good one? Like 7 cubed would be 7 times 7 times 7, right? So if your exponent's negative, though, the way that works is that instead of repeatedly multiplying that number, you're going to repeatedly divide that number. So if this was like 7 to the negative 3, it'd be like 1 divided by 7, divided by 7, divided by 7, which would be 1 over 343. So number 7, we've got 4 squared is 16. That one's pretty obvious. Here we've got another negative exponent. So this would be like 1 divided by 9, divided by 9. So here we get 9 to the negative second power is 1 over 9 squared, which is 81. So that one checks out. Number 9, we have another negative exponent. Now, also in number 9, notice how there's no base written here. Okay, whenever there's no base written here, the base that is assumed is going to be 10. Okay, so there's like a little 10 here. Okay, that we typically do not write. Log base 10 is also known as the common logarithm, or the common log. So we've got 10 to the power of negative 3, which is equal to 1 over 10 cubed, right, which is 1,000. So that one works out as well. And I think all these are going to work out nicely. For number 10, we've got 32 to the power of 2/5 equals, is that 4? Yeah, that's 4. So this one I might check in the calculator just to make sure that that's correct. I also want to show you how we can write this using radicals rather than as a rational exponent. Either way is fine, but I think it's worth bringing up just so that you can see that they are in fact equivalent. So let's see, we got 32 to the power of 2/5, which is 0.4 if you just want to type it in as a decimal. So I'll leave it as a fraction. And we do get 4. Okay, so that does check out. So what I wanted to say about the radicals is that you could also rewrite this using a radical. So just as a little reminder here, going back to good old algebra days, and kind of box some of these rules here as we go along, is if you've got, we'll say, x to the power of, we'll just say a over b, just kind of give some letters in there. This is going to be equal to x to the power of a, and then the b is going to be our root. So it's not necessarily a square root. Square root implies that the denominator is 2 there. Well, this thing's covering up my thing. Oh, there we go. But we can take the, is it not going to let me do an nth root here? Let's see, come on. I think there we go. Okay, there we go. So we've got the bth root of x to the a. So in other words, the number in the numerator in your exponent is going to be the power, and the number in the denominator is going to be the root. So an alternate way that we can write this would be 32 squared, or the 5th root, rather. Let's get this all ready to go. There we go. Okay, so it would be the 5th root of 32 squared. Yeah, that's pretty much it. That does, in fact, equal 4. Another way you could write this is you could put the power on the outside if that's easier to do the root first and then the power. In this case, it might actually be easier to do that because the 5th root of 32 is 2, and 2 squared is 4. But trying to square 32 in your head could be a little tricky. So if you want to throw this square on the outside, that's fine too. The order of operations there doesn't really matter. So either one of those is fine. I'll usually just stick to the rational exponents, but I do want you to know that this is equivalent as well. That might come up later. So for number 11, we've got 16 to the 3/4 power is 8. This would be equivalent to saying the 4th root of 16, which would be 2. So the 4th root of 16, which is 2, to the 3rd power is 8. So that checks out as well. So either one of these is fine. For number 12, we've got 64 to the 1/2. Just kind of line these up so you can see them a little easier. So yes, we've got 64 to the 1/2 power. Anytime you have a power of 1/2, that's equivalent to just doing a regular old square root. So the square root of 64 is 8. So we know this is going to be true. If you want to try to rewrite it using this little rule over here, we would write it as the square root of 64. Whenever you don't see a number like right here in front of the root, in front of the radical, there's an implied 2 there. Okay, so that's the 2. A regular square root, you typically don't write that. And the same thing goes here, right? Like you don't usually write 64 to the 1st power, but you could if you wanted to, right? So these are just like the implied numbers that typically you're not going to write. Normally you just write square root of 64. And that's 8. Okay, so that's going from logarithmic form to exponential form. And after this, we're gonna go backwards. We're gonna go from exponential form to logarithmic form. So let's take a look down here. For number 13, 6 squared is 36. Yeah, I'm going to just go ahead and assume that these are all going to be true equations and just focus on the conversion here. So the base is 6, so we're going to have log base 6. Okay, I'm just going to kind of make a template here so that I can copy and paste. Oh, why is this not? There we go. So the log base b of, we'll say the power equals the exponent. Okay, so this is going to be my little cheat sheet over here. Okay, so here, and I'm even going to write base to make it really obvious. Okay, so remember that the logarithm is just the exponent. Okay, so here we'll have log, and the base here is 6. The power, if this thing will move out of the way, is 2, and it's 36, and the exponent is 2. So for number 14, we're going to have log, the base is 12. Gosh, this thing's kind of getting in the way here. The power is 1, and the exponent is 0. For number 15, we'll have log base 16. Oops. Of 1/16. Now, if it's more than just one number, I'm going to put in parentheses here. 1/16, just to make it a little bit more obvious, separate it out from this, this base here. And then the exponent's -1. For number 16, we got the base, which is 5. The power is that fraction again. Anything that's a little bit more complicated than just a single number, and I'm going to put it in parentheses, just to make it easier to read. And the exponent's -2. For number 17, the base is 125. The power is 25, and the exponent is 2/3. Here, just want to point out real quick that 49 to the 1/2 power, like we talked about up here, whenever you raise something to the 1/2 power, that's just taking the square root of it. So the square root of 49 is 7. Just want to point that out. So log base 49 of 7 would be 1/2. For number 19, we have log base 5 of 25 is equal to 3. For number 20, we've got log base 13 of 160, is it 169? Yeah, 169 equals 2, because 13 squared is 169. For number 21, our base is 4. Our power is 1/64, so I'm going to put that in parentheses. You can really put them all in parentheses. If it's just a single number, it doesn't really help, I think. I think when it starts getting a little messy and you want to make it a little bit easier to read is when you want to put those parentheses in. It's really more of a stylistic choice, to be quite honest. And our exponent here is -3. For number 22, I normally would put log base 10, right, if I'm just sort of like going along and doing the same thing for all of these. But I'm not going to put 10 because when the base is 10, this is considered our common log, and so we typically do not write 10. If you don't see a 10 there, it is implied, okay? This is called the common log. So I'm just going to write log of 0.001 equals -3. Here, my base is 81, my power is 3. I didn't like that. Power is 3, and the exponent is 1/4. And for number 24, let's see what we got here. Our base is 9, and the power is 27, and the exponent is 3/2. So there you go. So this is going to be, done a lot of practice now, kind of going from logarithmic to exponential form and vice versa. Down here, we're going to be evaluating logarithms. So we're going to be answering the question like 4 to what power is 16? Okay, and that's how we're going to evaluate all these. So, let's go ahead and talk about it. So this little cheat sheet, I'm going to copy and paste this down here so we can kind of look at it as we go. But all right, so this right here is the base, and this is the power. So the question is, and just I'm going to keep hammering this, the logarithm is just the exponent. So we're looking for what the exponent is. In other words, 4 to what power is 16? That's what you're trying to find, okay? So since 4 squared is 16, we can say this thing equals 2. All right, for this one, 3 squared would be 9, 3 cubed would be, what would that be? 9 times 3 would be 27, and so this would be 3 to the 4th. So log base 3 of 81 would be 4. Here, you want to recall that the implied base is 10. So 10 to what power is 1,000? Well, 10 cubed is 1,000. For number 28, we have a natural log, and this is the first one in the homework that has a natural log. Just as a reminder, whenever you have natural log, that's called a natural logarithm, and that's going to be equivalent to when your base is Euler's number. Okay, so if this is what we're trying to figure out, e to what power is e to the 7th? Okay, this is like sort of the unconventional way of writing this, but that is essentially what that natural logarithm means. And so I'm going to go back to the question that I posed in number 25, which is the base, and I'll write this down here, the base to what power is e to the 7th power? And then when I kind of rewrite it like this, I think it makes it way more obvious what the solution is going to be here. E to the 7th power is 7. So this is just going to equal 7. Number 29, we've got 3 to what power is 1? Well, anytime you raise a number to the 0th power, it equals 1. So anytime you've got a logarithm where the argument inside the parentheses is 1, it'll equal 0. Okay, it doesn't matter what this is. The only, anything that is going to be a valid base here is going to equal 0 if the argument's 1. Because 3 to the 0 is 1, 4 to the 0 is 1, etc. For number 30, we've got 5. Here's one where I'm going to rewrite it. 5 to what power is 1/5? So we talked earlier about how negative exponents work, and so this would be like 5 to the negative first exponent. So this thing will just equal negative 1. Four to what power is 4? Well, anytime the base is equal to the power, then the exponent's just going to be 1. Anything to the first power is itself. So if you ever see these two numbers that are the same, then this logarithm is just going to be 1. Same thing's going on with number 32. It's just that the base is implied, right? When you just see log and no number in the subscript, it is implied to be 10, and 10 to the first power is 10. For number 33, kind of looks backwards, right? You might think, oh, 6 squared is 36, right? But what this is actually saying is 36 to what power is 6? Okay, so if you're thinking, all right, well, I know that the square root of 36 is 6, right? So let me write that down. We know that the square root of 36 is 6. How do we write square root as a exponent? This is something that we talked about earlier. I think it came up, where did it come up? Over here in number 12. Whenever you take the square root of something, that's equivalent to raising it to the 1/2 power. So this is just going to equal 1/2. So when your logarithms or your exponents are fractions that are less than 1, you'll see that the number becomes smaller, right? Like the power will be smaller than the base. So that's happening on, it looks like 34 and 35. So we're gonna kind of keep a lookout for that. So here, again, we're saying 27 to what power is 3? Well, we would say, okay, well, 27 is really like 3 cubed, right? 3 cubed is 27. So 27, like, if I were to raise that to the negative third power, that would be equal to like 1 over, I'm sorry, not negative third, but 1/3. Oh gosh. Let's try that again. 1/3 power. That would be equal to 3, okay? And that's because 3 cubed is 27. All right, so this is going to be, it's going to equal 1/3. Now, 35 is a little trickier, and I'm going to kind of approach it using a different strategy. 34 is kind of like on what I think of as like the edge of what you could reasonably kind of figure out in your head. 35, I feel like is kind of pushing that a little further. 64 to what power is 1/16? Now I think it's like not so obvious. So if you're ever stuck in trying to figure out what this is, one strategy you can take is to rewrite both of these numbers in terms of the same power. Okay, so like 64 is 4 cubed. And we're trying to raise that to some power. Okay, come on. I don't want to grab that. Why is this, what's going on here? One sec. Why is this not working? You know what? Here, I'll just try it like this. Where's my parentheses? I guess I just have to type it. Okay. Sorry for the technical issues here. There we go. So, in other words, this to some power is 1/16. Now, 1/16 is like 1 over 4 squared, right? And we said before, if this is like in the denominator, then this is equivalent to 4 to the negative second power. Okay, so now we're getting closer to a statement that might be a little easier to figure out. So we started off by saying that 64 to what power was 1 over 16, and I rewrote both of these using the same base. And so whenever you raise a power to a power, you multiply the powers. So one way that we could kind of think about this is 4 to the power of 3 times, we'll just call it x, equals 4 to the negative second power. And if these two bases are the same, we can just set the exponents equal to each other. So like 3x equals negative 2, and so x is going to be negative 2/3. So like I said, this one's not very obvious to figure out, just kind of in your head. I think this one kind of pushes you beyond what I could reasonably expect you to kind of figure out without setting up an equation and solving. And that's something we're going to work on a little bit more next time, is really hammering down how to solve equations like this. We're just going to kind of touch on it today. 36, kind of a similar deal here, where it's not super obvious, 5 to what power is equal to, I'm going to rewrite this right away and say 25 to the 1/3 power when you take a cube root like that. And so I'm going to approach it similarly to how I did number 35, which is to say 5 to some power, that's going to be the solution here, is equal to, now 25 is 5 squared, right? So, and 5 squared to the 1/3 power would be the same as like 5 to the 2 times 1/3 would be 2/3 power. Right, so now it's a little bit more obvious what the answer is going to be here. It's going to be 2/3. All right, well, these last two I know are a little trickier than the rest. We'll get a little bit more practice with these harder ones next time. But I just want to give you a little taste of how to evaluate some of these that are not, maybe not as straightforward as the rest. Okay, last section here, we're going to be rewriting these equations so we can solve for x. This is just going to be a little bit of an intro to what we're really going to focus on next time, which is solving these kinds of equations and solving more complicated equations. Number 37, really all we're going to do here is we're going to rewrite these either as exponential or logarithmic, depending on how they started, and see if we can't just figure out what the solution is. There are some more advanced techniques we can use that we'll learn in the near future on how you can do this. But like if I just rewrite this as 3 squared equals x, it becomes pretty obvious what the solution is just going to be 9. There's not a whole lot of algebra to do. We're just going to rewrite it, and then if we can figure it out, good. If not, we'll take the steps we got to take to be able to solve it. Here we have x squared is 81, so x is going to be 9. Well, we got 9 twice in a row there. How about that? Now, you might be wondering why I'm not including negative 9 in this, because, negative 9 squared is 81, but the only valid bases that I can have here are going to be positive, okay? You cannot have a negative log base. Just because when you have an exponential function, the base can't be negative, or else, you can have a function like that, but it's not going to be exponential. If you're curious about that, ask me about that in class, and we can go into a little bit more detail on why that is, if we haven't already talked about it. So number 39, we've got 25 to the 3/2 power. Okay, so this one we might need to kind of figure out here. We'll just take it step by step. Here we've got the square root of 25, which is 5, and then 5 cubed. Okay, so first, square root of 25 is 5. 5 cubed is going to be, let's see, 5 times 5 is 25, so that'd be 125. For 40, notice that we have a natural log, so our implied base is Euler's number. E squared is x, and that's all we can do there. We can't simplify this any further because e is an irrational number. For 41, we've got e to the x equals 10, and so when I rewrite this, I get the natural log of 10 is x. And similar to number 40, that's as far as we can go with this. This is an irrational number. You can type it into the calculator, and if you want to get a rounded answer, but the exact answer is probably better. 3 to the x equals 7. You might think, oh, well, it's got to be some decimal, right? Because like 3 squared is 9, 3 to the first is 3, so it's got to be somewhere in between there. But the answer is going to be, written as a logarithm. So we're going to have log base 3. Let's see. Log base 3 of 7 is x. And, just kind of like the last couple, we can't simplify this at all. This is just going to be our answer. For 43, we've got 10 to some power equals 12. That's going to be the natural log here. Normally I would write like log base and then whatever number this is. So like I would write log base 10, but 10 is our common log, so we don't have to write that. We're just going to say log base 10 of 12 is x. And finally, we get this really wild problem, e to what power is pi? There is a power that exists there. It's just irrational, and we could find it by rewriting this as a logarithm. So we've got the natural log, right? So it's log base e of pi. So the natural log of pi is x here. So there is a number there. You could throw this in your, if you're going from like 2.7 to 3.1, it's going to be a little bit above 1. I couldn't tell you exactly what it is off the top of my head, but it's going to be 1 point something. And there you go. All right, well, that's all the homework for tonight. I hope you all enjoy the video, and have a great day, and I'll see you next time.